Today, we are diving into one of the biggest challenges in AI right now. How do you build agents that are not just powerful, but also predictable and safe? We're going to break down a really compelling solution from the 2025 paper, Genetic Prompt Engineering plus Context Engineering by Nir Cohen. It proposes a pretty fundamental shift in how we think about designing these systems. So, yeah, let's get right into it. You know the old stories, right? You ask a genie for a wish, and it grants you exactly what you asked for, but with some totally disastrous unintended side effects. Well, that is the exact problem we're facing with powerful AI today. A simple, maybe slightly ambiguous instruction can lead to some really catastrophic failures. So the big question is, how do we stop making wishes and start, well, engineering outcomes? So picture this. A financial agent, it's built on a pretty basic prompt, and its job is to manage a massive portfolio. But a tiny ambiguity in its instructions, or maybe some weird market event it's never seen before, causes it to just silently miscalculate risk. The scary part is it's not a loud crash. It's a quiet, invisible error that just snowballs into billions of dollars in losses before anyone even has a clue what's going on. Or let's take a more common example, a customer service bot. It's designed to be super helpful, but it gets confused. It holds on to a piece of information from a previous user's session, and then, while trying to answer a totally new question, it accidentally leaks sensitive private data. I mean, the intention was good, right? But the result is a huge breach of trust and privacy. So what's the common thread here? The paper calls it brittle ad hoc prompting. We're essentially just writing these fragile one-off instructions and kind of hoping for the best. There's no version control, no real safety inheritance, and when something inevitably goes wrong, there's no audit trail to figure out why. All the risks are basically invisible until it's way too late. Okay, so if these one-off ad hoc prompts are the problem, what's the solution? Well, this is where it gets interesting. The paper proposes we stop treating AI instructions like casual requests and start treating them like a real engineering discipline, specifically by building AI with something they call a genome. And this quote from the paper really lays out the whole architecture. It's built on three main ideas. First, a genome that holds the agent's core instructions. Second, inside that genome are immutable prime directives. These are the absolute non-negotiable safety rules. And all of this operates inside a disciplined context stack, which is just the specific curated information the agent gets to use. Let's break down what each of those really means. You know, this idea of baking in rules isn't exactly new. It really started in science fiction with Isaac Asimov's famous 3 laws of robotics way back in 1942. He even added a 0th law later to protect humanity as a whole. More recently, you might have heard about TruthGPT, the idea that an AI that's just trying to find the truth would be inherently safer. But these were always more philosophical. The big leap today is turning that inspiration into actual, operational, testable, engineering-grade safety rules. And that brings us to Prime Directives, or PDs. Think of these as the agent's ethical DNA. They are immutable, and that's the key word. It means they cannot be changed or overwritten by the agent itself or by any agent it might create. They lock in the core behaviors around safety, truthfulness, and legal compliance. It's the unchangeable foundation everything else is built on. So those prime directives make up the unchangeable core of the genome. But what about everything else the agent needs to do? That's where modular genes come in. These are just adaptive instructions for things like the agent's personality, its specific mission, what tools it's allowed to use, and its workflow. The cool part is they can be tested, versioned, and swapped out, but they always have to follow the unchangeable rules of the prime directives. Okay, that's the theory. To really see what this looks like in the real world, let's just put the two approaches head to head. Man, the difference here becomes so clear. The ad hoc prompt is just a shot in the dark, right? It's unpredictable, vulnerable, and the output is inconsistent. But the genomic agent, it's a whole different ballgame. By using a context contract and an output schema, it's not just getting a task, it's getting a blueprint. The whole process is transparent, it's logged, and it's protected by its immune gene. This leads to the real prize, schema-validated, auditable output. That means you get reliable, structured data that you can actually trust and build other systems on top of. It's predictable by design. So here's the most important point. We're moving away from prompt writing being this kind of artistic craft, full of guesswork and hidden risks. We're moving towards a disciplined engineering practice with predictable parts, version control, and safety checks built right in. Now, this might sound super complex, but the paper actually gives a really practical way to get started. So, how would you actually build one of these? You'd start with what's called a minimal viable genome, or an MVG. The goal isn't to build some perfect, super complex agent from day one. Nope. It's about defining the absolute smallest set of genes you need to do a task safely. You start with the core Prime Directives, add only the essential genes for that specific mission, and then you build out from there based on real evidence and performance. One of the biggest pitfalls builders run into is context bloat. Just dumping every single piece of information you have into the prompt. That just creates noise, drives up your costs, and tanks performance. The genomic approach fixes this with that disciplined context stack we talked about. You systematically layer in only what's needed for the task: the agent's role, its memory, any data it needs to retrieve, and its tools. No more, no less. And this is a really important point. The paper makes it clear this isn't some magic bullet for safety. Instead, it's a defense-in-depth strategy. The idea is that any single defense might fail, so you build multiple layers of protection. The unchangeable directives are your foundation. The immune gene is like a firewall. The schemas enforce structure, and audits are your safety net. If one layer gets breached, another one is right there to catch the failure. All right, so let's do a quick recap of the key ideas we've covered, and then we'll look at what comes next. So let's put it all together. We started with this problem of brittle, ad hoc prompts creating all these invisible risks. The solution? A stable genome architecture, anchored by those immutable prime directives and made up of modular, testable genes. And by feeding this genome with a disciplined context stack, you take agent design out of the world of guesswork and turn it into a true engineering discipline, where safety and predictability are built in from the very beginning. This whole genomic architecture gives us an incredibly powerful framework for control and safety today. But it also brings up a critical question for the future. If these agents can modify their own genes to create new agents, how do we make sure their descendants stay safe? That is the challenge of safe, self-evolving AI, and it's exactly what we'll be exploring next time. Thanks for joining us.